Up until this point in our series on limits, we've talked about quite a few things, from limits and what they actually mean in approaching, not equaling, to the difference between left, right, and two-sided limits, and to intermingling limits with infinity. All three of these topics are vitally important, but yet there's one other topic that we have yet to look at that is, I would say, even more important than these. What is it that you might ask? Well, in this three-part finale in our series on limits, we're going to be reviewing the laws of limits. Arguably the most important aspect to anything we will learn about limits, and although some of the rules can be a little challenging, it opens the door to solve any limit. So without any further ado, let's go ahead and take a look at our first law of limits. Now for the first two laws of limits, I would like to put a small emphasis, but not a huge amount, because these rules are pretty obvious. But the first rule I'd like to go over is the constant rule of limits. That we need to let c be a constant, or otherwise just one fixed number. And this rule says, the limit as x approaches some number of a constant c, then the answer to that limit is always c, meaning the limit of a constant is itself. Now this makes total sense, because if I go ahead and I draw a graph, we can visualize this rule pretty easily. So suppose I had a constant, let's pick y equals 2, and I'm told to find the limit as x approaches a number of the constant 2. What does that equal? Well, the blue line that's on our graph here represents the line y equals 2. And so we said x approaches a number, but what if we said x approaches 3? If we approach x equals 3 right here, well, what does our y value equal? Well, it equals 2. How about if we said x approaches negative 3? Same deal. Negative 3 right here, it also approaches 2. And this even works for decimals and for irrational numbers as well. If I said x approaches the square root of 2, that would be approximately right here, but yet even at that location, the answer is still 2. Why? Because it's always a flat line. There's no change. So therefore, the limit as x approaches n of 2 is always going to be 2. Like I said, it's really straightforward. And this next law of limits is no different. Now the next rule we're going to look at, also I don't want to spend too much time on because it's very specific, but it's kind of a quick, easy rule to get down, and that is the y equals x rule. And this rule only applies to the function y equals x. And this limit says, limit as x approaches a number of x. Now, I know I'm not including y, but the idea is y equals x. Then the answer to that limit is always x. And it kind of piggybacks off of the last rule that we just looked at. However, the only difference here is that x is not a constant, meaning that it can change over time, or if you can decide to move it at any point you want. It's more easily explained if I showed you on a graph. Okay, so now here in front of us, we have the graph of y equals x. Specifically this line. This does not apply to other lines, so just keep that in mind. But if we were told to take the limit as x approaches a number of y equals x, then that should equal the number we're talking about. So let's pause for a moment and take some examples here. Let's say that as x approaches 2. Okay, so we go to our line, we find, okay, here is x equals 2, and wouldn't you know, the corresponding y value equals 2. How about let's find the limit as x approaches negative 4. Here we are, right where x equals negative 4, and if we just go right on down to around that point, then wouldn't you know it, the corresponding y value is also negative 4. That is one of the core fundamentals of this line, is that whatever x value you plug in, you will always approach the same y output, because literally the function says it, y equals x. So hopefully it's a little more clear why the limit as x approaches a number of y equals x, then that equals x. It equals itself. And the last rule we're going to look at today is the limit sums rule. Now is when we really start getting into the meat and potatoes of the matter. Now there are two ways we can write this same rule, but it's contingent off of one idea. We need to let f of x and g of x be functions, and that the limit as x approaches a number of f of x equals some number L and the limit as x approaches some number of g of x be equal to m. Now the first way to write this rule is as follows. If I have the limit as x approaches a number of f of x plus g of x, then that limit equals L plus m. The second way to write this rule, and I would say is a little bit easier to remember, is limit as x approaches a number of what we had earlier, then that equals the limit as x approaches a number of f of x plus the limit as x approaches the same number of g of x. Essentially, the only difference between these two is the fact that we're substituting L for limit instead. It's a little bit longer, but for me, this is a little easier to remember. But I know this absolutely looks really big and kind of scary. But don't worry, the idea is very simple. We'll take a look at some examples right here. So before we even go to try to solve any of this, we need to identify what are the functions that we're dealing with. Well, here it's pretty obvious. Of course, we have x cubed, and we can call this f of x. And the other one, the cube root of x, we can call g of x. And then so we can go ahead and write that down accordingly. So why is this step important? Well, here, it's pretty obvious. We have two distinct functions right there, but there are others that it's a lot harder to tell. So you need to take some more time to just quickly analyze which functions we're dealing with before we even try to solve it. So now that we've identified each of the functions, let's go ahead and break the limit apart. So the limit stays with us as x approaches infinity of x cubed. Now the only thing that's going to really stay here is the plus sign, but make sure it's distinct from our function. We don't want to mix the plus sign up with our limit. And then the other side, we have the same limit, again as x approaches infinity. But instead of x cubed, we're doing the cube root of x. Okay, now that we have our limits broken up respectively, now it's a lot easier because we can just focus on one at a time instead of both at the same time. So what about x cubed? As x approaches infinity, as basically as x gets bigger and bigger, what happens to x cubed? Well, x cubed is a basic polynomial function, or I should say in this case, a monomial function, and really any polynomial approaches positive or negative infinity at some point. Now here it's pretty obvious because we're going to infinity, we're making x bigger and bigger, so limit as x approaches infinity of x cubed is positive infinity. Don't forget the plus sign. Now how about the cube root of x? Well, with the cube root, we don't have really the same problems as with the square root. Because remember, we cannot take the square root of a negative number, but with a cube root, it's fine. And since we're going in the positive direction, x approaches infinity, if x gets bigger and bigger and bigger, what's going to happen to the answer? It's also just going to get bigger and bigger and bigger, meaning that our answer to that is also infinity. And infinity plus infinity, well, that's pretty obvious. The answer is infinity. And so we can confidently say the limit approaches infinity. Let's take a look at another example. All right, so we have another example right here, and we're saying limit as x approaches 256. So not infinity this time, which makes it a little bit easier. Now, just like last time, we need to identify an f of x and a g of x. Not too hard here. This one, fourth root of x, we'll call f of x. And this one, log base 2 of x, we'll call g of x, and jot that down accordingly. So now that we've identified our functions, let's go ahead and break the limit up. So this one's a little bit easier because not only are we having x approach a finite number, are there any places where a denominator can be 0 or we're taking the log of a negative number? Absolutely not. What that means is that we can literally just substitute 256 for x. All right, so what is the fourth root of 256? Well, the square root of 256 equals 16, and if we take the square root one more time, which is basically the same thing as saying fourth root, then we get 4. So the fourth root of 256 is 4, and we're going to add that to log base 2 of 256. In other words, 2 to the power of what equals 256. Well, if we start with 2 and continue multiplying by 2, it'll take 8 times for us to get 256. And of course, lastly, we can add these together and get 12. So the limit as x approaches 256 equals 12. Let's do one more, and then I think we'll be good for today. So, looking at this final example for today, we're seeing the limit as x approaches 2. Now this one, it's the same thing as last time, but here it's a little bit trickier. Which one is our f of x and our g of x? Well, our f of x wouldn't just be x minus 2, not quite, nor would it just be x, since that would invoke a quotient law of exponents. We're not quite there yet, but definitely stick around. Same thing for g of x. No, rather, our f of x is the entire fraction. How about over here? Anything different? Well, that wouldn't really work out, so the entire fraction itself is going to be g of x. Well, before we get a little too ahead of ourselves, I want to take a note of this minus sign. Of course, subtracting isn't addition, so what's the difference here? Well, in reality, it's not any different. We can still start with the same function, and subtracting is the same thing as adding a negative. So really, there's actually nothing different between the top and the bottom that we see here. The only thing is that you gotta remember to account for the negative in your answer, if it's necessary. So now that we know our f and g of x, let's go ahead and break it down. Okay, so in both limits, we're taking the limits of rational functions. So of course, we need to just see if we can plug x in directly. Well, but in here, we would get 2 on top, sure, but on bottom, we would get 2 minus 2. And so that would equal 2 over 0. And remember, having a denominator of 0 is not a good thing. But before we just can assume that it goes off to infinity without an asymptote, remember what we have to check. Is there any possibility for the top and the bottom to cancel out? Well, in the case of x over x minus 2, not really. What does this mean? Well, this means that, as a matter of fact, x over x minus 2 does have an asymptote. Editor's note here. For the sake of the problem, I'm going to go ahead and add from the left on each of the limits, just to clarify that we are coming from the left side, because in this case, coming from the left would go down and coming from the right would go up. And as we've seen before, left and right-sided limits have to agree. But anyways, back to the video. So now that we know our x over x minus 2 has an asymptote, what happens as x approaches 2 from the left? Well, from the left means that everything else has to be less than 2. So that would be like 1 minus 2, 1.9 minus 2, so on and so on. Meaning that all the answers are negative. And so limit as x approaches 2 from the left is negative infinity. How about x approaches 2 from the left right here? Now, if we plug in x equals 2 to x on this time, instead of getting 2 over 0 like we saw earlier, what happens? Well, we get 2 minus 2 over 2. So instead, this is 0 over 2, not 2 over 0. So this is actually okay if we plug into 2 like that. And as we saw, we get 0 over 2, which is 0. So what we're looking at here is negative infinity minus 0. And what happens when you subtract nothing from negative infinity? Well, it's still negative infinity. So as a matter of fact, that approaches negative infinity. So what are some of the key takeaways that we've learned today? Well, we've learned that the limit as x approaches any number of some constant c equals the constant itself. And this makes sense because a constant, guess what, remains constant. We also took a look at the y equals x rule of limits. And that rule says if we take the limit as x approaches a number of y equals x, then we get the same value out. Sorry, that's x and y, not x, Andy. And then lastly, we talked about arguably the most important one today, and that is the limit sum rule. So why is this rule so handy? Well, it takes more complex overall functions, like if we call this h of x, and it breaks them apart. So now instead of solving one giant limit, we can solve 2 smaller limits. And so of all the rules here today, I would highly recommend that you continue to put some effort into this addition rule, which also works for subtraction. So stay tuned because next week will be our part 2 of our laws of limits. And make sure to keep working hard, don't give up, and you got this.